Okay, we are continuing our study of fatty acid synthesis. This particular time, we want to look at how the biosynthetic pathway is regulated. Now, you know that for any metabolic pathway, the body has to find a means by which the processes or the reactions within the pathway will be regulated, so that let's say if it is synthesis or whatever it may be, whether it be synthesis or let's say a breakdown, then there should be something that will trigger what an increase in synthesis or a reduction. Probably if you have too much of the product that we want, then we what regulate the rate of the synthesis, or if the breakdown products too are obtained in higher quantities, you can also what regulate how what the breakdown occurs. So a lot of factors are to play into how those biosynthetic pathways, or be it also a catabolic pathway, will be regulated. Now, same thing applies to fatty acid synthesis. We cannot continuously be synthesizing fatty acids, right? A time will come that we have too much of our product, that's palmitoyl. The body needs what to balance what molecules, or let me say these substrates. As you are producing, we should also be seeing what usage, so that there is a balance between the anabolic, and then what the catabolic pathway. So how does the body take care of this the regulation of this biosynthesis? We are looking at it at the level of two enzymes. We are looking at it at the level of two enzymes, which is the acetyl-CoA carboxylase, and then we'll come to fatty acid synthase. Now, we made mention of the fact that acetyl-CoA carboxylase catalyzes the rate determining step of what FA synthesis, fatty acid synthesis. So it is a good point to regulate the synthetic pathway. Now, there are different ways by which we can have this happen. One, we have what we call feedback inhibition. Feedback inhibition. So in this case, the products the product that is formed from fatty acid synthesis comes back to inhibit the action of this acetyl-CoA carboxylase. So we know that at the end of fatty acid synthesis, we are going to get palmitoyl CoA, right? Yes. So if there is too much of this, if there is too much of palmitoyl-CoA, you have synthesized, yes, the requirement that we needed to meet has been exceeded. Then if there's too much, we'll go back and then inhibit this enzyme. And so that means that if the rate determining step, we are not able to achieve the formation of malonyl CoA, will not be able to form fatty acid. So that's one, feedback inhibition. There is one other one. You have allosteric activation. Allosteric activation. Now, we made mention of the fact that acetyl-CoA carboxylase acts in the polymeric form. So for it to be able to synthesize malonyl CoA for us, it should move from the monomeric to the polymeric form. Now, one thing that helps in this process is citrate. So they say that citrate favors the polymeric conformation or form of acetyl-CoA carboxylase, so that in that polymeric form, it is able to adapt the carbonyl group that we are going to take from bicarbonate and then add it to acetyl-CoA so that we can form what? Malonyl-CoA. Now, one other thing we would like to look at, that's number 3, is hormonal regulation. Hormonal regulation. So there are 2 states that we would like to look at over here. We have one, phosphorylated states of the enzyme, and then what? A non-phosphorylated or unphosphorylated. Unphosphorylated. Now, the active state of the enzyme is what? Not phosphorylated. So there is no U4 minus what? In addition to complex to the enzyme. Immediately you add this to the enzyme, that's in a phosphorylated state, and it becomes what? Inactive. So it is a way to be able to regulate the action of the enzyme. Now there are some hormones that favor the phosphorylated state of what? This enzyme. So we have a hormone like let me pick this. So a hormone like glucagon, and then epinephrine. And then you have adiponectin. So glucagon, epinephrine, adiponectin, they favor the phosphorylated state, the inactive state of the enzyme, so you'll not be able to synthesize fatty acids. Now, for the unphosphorylated state, one particular enzyme that is quite pronounced there is insulin. Remember that you need CoA, you need acetyl-CoA to be able to initialize the fatty acid synthesis, right? And then this acetyl-CoA is supposed to be obtained from pyruvate. And if you are going down, that will be what? From glucose. And then you have insulin dependent on glucose transport. Insulin is going to upregulate this formation of pyruvate. And in that sense, you are going to get a lot of acetyl-CoA, and then we can proceed into the formation of fatty acids. So these three levels are able to regulate the action of acetyl-CoA carboxylase, and in essence regulate the extent of formation or the rate of formation of fatty acid. Now let's move to the fatty acid synthesis. Now we want to put this into 2. We have the short term, and then you have long term. So if you have a short term one, this transient effect. Long term, they affect enzyme synthesis, right? They affect enzyme synthesis. So if it's either could be an increase in enzyme synthesis, or it could be a decrease, right? A decrease in enzyme synthesis. Now let's see something. Okay, so for the long term, let's say increase, right? Increase synthesis, increased synthesis. Things like having a diet that contains huge amount of what? A high carbohydrate diet. High carbohydrate diet, right? It will increase what? Synthesis of the fatty acid synthase. Number two, if there is presence of insulin, insulin can also what? Affect what? Cause an increase what? Synthesis of what? The enzyme. Now let's see decreased synthesis. If you take a diet that contains a lot of PFAS, right, polyunsaturated fatty acids, they decrease the synthesis of the enzyme. We have, let's say, glucagon over here. It can affect, although it also contributes a short-term effect. Then someone that is fasting, right? When you are fasting, the body needs what? To break down available fat source to be able to supply you with energy because you are not taking in what? Glucose. So there is no need increasing the synthesis of what? Fatty acid synthesis to be able to form what? Fatty acids again. The available ones even need to what? To be broken down, and then have fatty acids what energy available for the body to be able to go about some metabolic function. So in fasting, in a fasting state, there's what? Decreased synthesis. Then a low carbohydrate diet too will be able to, a low carbohydrate, so CHO diet, will be able to what? To decrease the synthesis of what? The enzyme. Then if you are looking at short-term, insulin will have a positive effect as in it will increase the action of fatty acid synthase. Glucagon is going to what? Reduce, right? Any compound, sorry, anything that will lead to the phosphorylation of the synthase is also going to what? Inhibit or reduce the rate at which what the enzyme is going to function. So you come across something like AMPK. So AMP dependent what? Kinase is going to cause what? Phosphorylation. The kinase is the transfer phosphate groups to the enzyme, and then it's going to what? Reduce. So this side are those who are going to increase the rate of the action of the enzyme. Glucagon, AMPK are going to stop that. And then when you have a long chain fatty acids, they also what? Affect the rate at which. So all this side, this part, glucagon, AMPK, the long chain fatty acids, they are going to what? Reduce the action or the rate at which this fatty acids. Then the action is transient, right? Because they will not affect essentially the synthesis. But when it comes to this side, a long-term effect, say we have high carbohydrate diet and things, they will induce what? An increased synthesis in the number of enzymes, and then be able to increase the synthesis of fatty acids, or depending on the conditions that are available, there will be decreased what? Synthesis. Okay. Now, there is also a way that the body is able to coordinate the synthesis and then the oxidation pathway. So mind you, the body needs palmitoyl-CoA, right? Palmitoyl-CoA for some very salient function. And then when it is produced, if the body doesn't have any mechanism to prevent it from being like oxidized, it will just be taken through what? Into the mitochondrion and then oxidized. And in essence, you have lost what you produce, a constant antigen. So the body does something. Now, malonyl CoA, which is produced by acetyl-CoA carboxylase, inhibits an enzyme that catalyzes the rate determining step of fatty acid oxidation. So the beta oxidation that might have come across. what it does that it inhibits CPT1, which is the carnitine palmitoyl, right, transferase 1. So this is present on what? A membrane of the mitochondrion. And as soon as it takes up palmitol and then it sends it to what? Matrix of the mitochondrion, oxidation will occur. So in order to prevent us from going through a cycle where we will not get the product that we want, or after production and then it is consumed by oxidation, then malonyl-CoA goes and inhibits what? This particular enzyme, so that it is not able to what? To take up the palmitoyl-CoA and then commit it into what? The oxidation pathway. In that case, we have palmitoyl-CoA over there, and then whatever function that we prefer it to be involved, or whatever process we prefer it to be involved in, that process could what? Okay.